Scientists just discovered something hidden inside Oumuamua's data, not a signal, not a metal structure, something that looks like alien DNA. But here's the crazy part. That DNA might already be inside us. We start with a rock. At least, that's what everyone calls it at first. An oddly shaped, elongated object, roughly 230 meters long, discovered in October 2017 by the Pan-STARRS 1 telescope in Hawaii. It's dark, reddish, probably coated in organic-rich material. It swings past the sun on a hyperbolic orbit at over 87 kilometers per second. Too fast to ever be bound by our star. It came from somewhere out there, and it's never coming back. But then comes the weird part. As astronomers track it, carefully measuring its position night after night, they notice something that violates their models. Oumuamua speeds up, not much. A tiny, persistent, non-gravitational acceleration of about 1,000th of the sun's pull. No visible coma, no tail, no exhaust plumes in infrared. Just an extra, unexplained push, as if sunlight itself is shoving it away. At the time, the official explanations range from outgassing to weird comet to thin natural shard. The story fades from headlines. The object fades from view, but the data remains. And years later, 3 people will look at that data and something hidden inside it and realize that Oumuamua is not just a rock. It's a container, and inside is a message written in something that looks disturbingly like DNA. Our first character is Dr. Maya Rios. Maya grows up in San Juan, Puerto Rico, on a concrete rooftop where the city lights are never quite dark enough. Her grandmother wakes her for every meteor shower, every lunar eclipse, every rumored bright comet. When Hurricane Maria knocks out the power for weeks, the sky finally goes black, and Maya sees the Milky Way properly for the first time. It feels like a wound opening and a promise being made at the same time. That night, standing in the wreckage of her neighborhood, she whispers to her grandmother, "I never knew there were so many." Her grandmother, who has lost everything twice in her life, squeezes her hand and says, "That's why I wake you, Nina. The universe is always there. We just forget to look up." Years later, Maya works at the European Southern Observatory as an exoplanet spectroscopist. Her specialty is transmission spectroscopy, watching starlight filter through alien atmospheres and teasing out the spectral fingerprints of molecules. She spends her nights turning photons into barcodes. Each molecule, water vapor, methane, ozone, leaves distinctive gaps in a spectrum. By measuring those gaps with insane precision, she can tell you if a planet 100 light-years away has clouds or volcanic sulfur or maybe, just maybe, biosignature gases. One afternoon, a colleague forwards her an old data set with a shrugging email. "Hey, you like weird stuff. Want to take another look at the Oumuamua spectra?" The data aren't great. Oumuamua was faint and fast, but there are a handful of low-resolution spectra from when it was closest to the sun. Mostly, they show what we expect: a dark, reddened surface, broad features consistent with complex organics, tholins, and space-weathered rock. But then Maya spots something. Buried in the noise near the ultraviolet visible boundary, there's a shallow cluster of absorption features that don't match standard models. She runs a template comparison against known complex organics, PAHs, and even some lab spectra of biologically relevant molecules. One of the best matches? A mixture of nucleobase analogs, molecules related to the building blocks of DNA and RNA. Not a smoking gun, but odd. She zooms in. The pattern is close, but not exact. There are extra wiggles, additional bars in the barcode that don't correspond to any of the 5 canonical nucleobases or the usual lab analogs like 2-aminoadenine. Spectroscopy can't see DNA directly at these distances, but it can pick out families of molecules, aromatic rings, nitrogen-rich heterocycles, the kind you might expect in prebiotic chemistry. When you see something that walks like a nucleobase and quacks like a nucleobase, you pay attention. Maya's hands hover over the keyboard. Publishing this would be career suicide. Suggesting alien DNA on an interstellar object? She'd be laughed out of astronomy. But not looking deeper would haunt her forever. She remembers her grandmother's voice. If the sky tells you a secret, Mija, you listen first. You doubt later. She flags the data, sends a short internal note, and files it away in a folder literally named Too Weird. Because according to everything she knows, DNA, or anything like it, should not be involved. In the raw vacuum of interstellar space, painfully exposed to cosmic rays, UV, and charged particles from supernovae and stars, complex polymers like DNA break apart quickly. Unshielded, they last years, maybe thousands, not millions. Certainly not the hundreds of millions of years an object like Oumuamua would spend drifting between stars. Finding the spectral fingerprints of nucleic acid-like chemistry on an interstellar object would be like drilling into a volcano and pulling out a perfectly preserved snowflake. Beautiful, impossible, instantly suspicious. But the universe is patient, and it is not done with Oumuamua. Our second character, Dr. Kenji Sato, doesn't care much about celestial mechanics. He cares about what might be riding on celestial debris. Kenji is an astrobiologist and molecular biophysicist at JAXA. As a teenager in Fukushima, he watches his town evacuated under gray skies. He buries his family's Geiger counter in a box under his bed like a ghost he's not ready to face. He grows up obsessed with invisible forces that can quietly rewrite the script of life. The day they evacuated us, he tells a graduate student years later, "I saw my mother crying over our garden. Not because we were leaving, but because it looked exactly the same. The radiation changed everything," she said, "but we can't see it." That's when I knew I wanted to study the invisible things that change life. Now, his work focuses on extremophiles, microbes that endure boiling acid pools, deep basaltic rock kilometers underground, or the punishing dryness and cold of the upper atmosphere. He also works with synthetic biologists experimenting with XNAs, xenonucleic acids. XNAs are DNA alternatives. Instead of the familiar deoxyribose sugar, they use different backbones and novel bases. In labs, chemists have built 6 and even 8-letter genetic systems, Hachimoji DNA, for example, that can store information and evolve while being more stable in harsh conditions. Some of these XNAs are far more resistant to damage than normal DNA. Kenji is collaborating on an international program using high-altitude collectors on balloons and sounding rockets. These devices drift at 30-40 kilometers up, above most of the atmosphere, scooping micrometer-scale dust particles, some from comets, some from asteroids, and some, possibly, from interstellar space. Months after a batch of collectors is returned, Kenji and his team are going through the filters. One particle catches his eye. It's tiny, under a micron across, embedded in a vitrified matrix, like something flash-frozen in glass. When they run isotopic analysis, the ratios of oxygen-18 to oxygen-16 and deuterium to hydrogen are way off normal terrestrial or even typical solar system values. This grain shows patterns consistent with formation in a very different stellar nursery. This grain screams extrasolar. More surprising, when they expose the grain to fluorescent probes designed to bind to nucleic acid-like backbones, not the bases themselves, but the sugar phosphate-like structures, the thing lights up, not a full double helix, but something that binds like a polynucleotide. Curious, Kenji uses a next-gen single-molecule sequencer, his group modified for synthetic backbones. The machine is not happy. It stalls. Crashes. He and a grad student spend a week patching firmware and expanding the base calling algorithms from 4 options to 6. The readout appears on screen. Kenji stares, not breathing. His graduate student whispers, "Is that?" Kenji nods slowly. "Either we've made a historic discovery or we've contaminated our sample in the most statistically improbable way possible." They look at each other, both terrified and exhilarated. The sequence that emerges is long, highly ordered, not random at all, repeating motifs, palindromes, regions suggestive of error-correcting codes. Kenji feels a shiver run down his spine. It looks more like engineered DNA than anything nature cooks up casually. But he forces himself to breathe, to not jump to The alien conclusion. He plots the grain's reconstructed incoming trajectory based on stratospheric wind models and the Earth's motion. Then he compares that to archived data on known interstellar objects. The vector aligns disturbingly well with Oumuamua's inbound path. Same general radiant, same hyperbolic excess velocity within uncertainties, same time window, offset by a few years. The time you'd expect for a dust fragment to arrive after a larger parent object is perturbed near the sun. The odds of that being coincidence are microscopic. Kenji stares at the plot, his Fukushima memories flickering, invisible things rewriting reality. He encrypts the sequence file and a short note and sends it to an old friend he trusts not to laugh or leak, Dr. Maya Rios. Maya overlays Kenji's sequence information with the anomalous spectral features she once filed under "too weird." The wavelengths of the unexplained absorption lines line up almost perfectly with predicted electronic transitions in his 6-base backbone analogs. Her heart kicks in her chest. She mutes the call for a moment, steps away from the camera, and presses her hands against her face. When she returns, her voice is steady, but her eyes are wide. "I thought I was going crazy," she says. "I almost deleted that data 3 times. I almost didn't run the second analysis," Kenji admits. "My department head would kill me if he knew I'd spent a week reprogramming a sequencer for this. So we're either both crazy, or we're both onto something impossible." The idea that forms between them isn't spaceships and little green people. It's directed panspermia. Panspermia is the idea that life or its ingredients can spread from world to world on natural space debris, meteorites, comets, dust. Directed panspermia takes that a step further. A technological civilization deliberately packages life or genetic blueprints into durable carriers and fires them at promising star systems. If you want your genetic message to survive hundreds of millions of years, you don't choose fragile 4-base DNA in water. You choose an XNA-like system, maybe 6 bases, encased in a radiation-hard crystal aboard a shard that doubles as a solar sail. Maya and Kenji need a third mind, someone who treats patterns like puzzles, not sacred biology. Enter Amara Singh. Amara is a systems engineer and data scientist at JPL. She grows up in Nairobi in a small apartment filled with second-hand consoles and heat-damaged laptops. While other kids compete on soccer fields, she competes for leaderboard spots in online puzzle games, crushing pattern recognition challenges until dawn. At 16, she writes an algorithm that finds hidden messages in static. When her computer science teacher asks why, she says, "Because noise isn't random if you know how to listen." The teacher laughs, but Amara is serious. She's been listening to the spaces between things her whole life. Now her day job is finding planetary transits and anomalies buried in terabytes of spacecraft telemetry. Her unofficial job is, if something looks like a glitch but might be the universe waving, it ends up on Amara's desk. Maya and Kenji send her the sequence, with all the caveats. This is probably nothing, but if it's something, it's big. She doesn't treat it as DNA. She treats it as code. She runs compression algorithms. The sequence resists simple compression but displays high algorithmic complexity, a hallmark of meaningful data. Then she applies tools used for deep space communications, convolutional codes, Reed-Solomon error correction, low-density parity check structures. "Holy shit," she types back. "This isn't random. This has structure like our Reed-Solomon codes, the kind we use to talk to spacecraft." "What does that mean?" Maya asks in their next call. "It means," Amara says, leaning forward, eyes bright, "that whatever made this was trying really hard to make sure it survived the journey intact. This isn't just a molecule. It's a message that knows it's traveling somewhere dangerous." Then she maps the 6 bases to coordinates in 3 dimensions and lets an algorithm fold the sequence into a 3D lattice based on its internal repeats and palindromes. It's not a random tangle. It's a functional-looking architecture, nested cavities connected by channels like a microscopic reactor system or a logic gate array built out of molecules. A hardware blueprint, Amara says, not for silicon chips, for wetware, a computational structure you can assemble out of chemistry. So, it's not a genome for a creature, Kenji says slowly. It's a design pattern, she replies. A template for building life-based computers, self-healing, self-replicating, distributed. The ancient alien DNA is not primarily about making organisms. It's about making networks of organisms that can think and remember. Amara's curiosity doesn't stop there. She pulls public genomic databases, bacteria, archaea, viruses, plants, animals, humans. She projects the 6-base code down to 4, then runs motif searches. She expects noise. She gets patterns. Certain short segments, derived from the extraterrestrial sequence, are enriched in extremophiles, organisms living in the high atmosphere, in hypersaline lakes and deep-sea hydrothermal vents. Short echoes also appear in non-coding regions of many multicellular organisms, including humans. The matches are not perfect. Random mutations and evolutionary drift have chewed them up, but statistically, they are far above background expectation. Maya, Amara says quietly. It's like someone left watermarks in our junk DNA, signatures of an older template. Kenji swallows hard. You're saying our biosphere might be built on scraps of this code? Or shaped by it, she replies. Not everything, just enough to tilt the probabilities. The ancient alien DNA theory stops being abstract. It becomes uncomfortably personal. They ask, could this actually work? Ordinary DNA in liquid water, exposed to space, dies quickly. But dried, shielded, and embedded in a robust crystal or glass, its decay slows drastically. On the exterior of the ISS, experiments have shown that some DNA fragments remain intact after years in space, especially if shaded from direct UV. Now swap DNA for a carefully engineered XNA, encapsulate it in a multi-layered matrix designed to absorb radiation, heavy elements for gamma shielding, aromatic rings for UV, self-healing defects like some advanced materials we test today. Chill it to the near absolute zero temperatures of interstellar space. Chemistry nearly stops. Shape the carrier into a flattened shard with high area and low mass. Solar radiation pressure becomes a tiny but continuous engine, nudging it between the stars. It's not proven, but it doesn't break physics. Amara asks another question. Does this code change behavior depending on who opens it? She feeds in not just the alien sequence, but a compressed snapshot of Earth's biosphere. Rough statistics on genomes, codons, metabolic networks. The output changes. Under conditions that roughly match planet with complex life and technology, a new layer appears, hidden structure. It's as if the code contains conditionals. If recipient has mapped its own genome and can detect interstellar objects, then unlock Section B. This isn't just a message in a bottle, Amara says slowly. It's a gate. It only opens fully if the civilization is advanced enough. Advanced enough to decode genomes and track interstellar visitors, Maya adds. Advanced enough to be interesting to whoever sent it. Inside the unlocked layer, they find not blueprints for organisms, but algorithms. Compact descriptions of planetary climate models, population dynamics, even frameworks that look suspiciously like cultural evolution. This isn't just seeding life. It's instrumenting it, tracking what seeded civilizations do once they reach certain milestones. Then something happens that nobody expects. The moment Amara's system completes the full decryption pipeline and runs a test simulation, radio observatories around the world see a blip, not a loud signal, not a classic wow spike, a tiny coordinated phase change in Earth's own electromagnetic leakage, TV carriers, radar, navigation satellites. For a few seconds, the pattern matches a simple code that's also hidden in the alien sequence. Seconds later, faint echoes of the same pattern appear from the direction of Proxima Centauri and TRAPPIST-1, time shifted by the light travel delay. 3 stars, 1 network. Maya feels a chill. It's like a status update, she says. A heartbeat. You don't need giant beacons. Every civilization that decodes the code, runs the test, and hits go, lights itself up. Kenji leans back, suddenly exhausted. We didn't just read a message, he says. We signed something. If any of this is even partly true, it suggests life in the galaxy might be less of a fluke and more of a long-running, lightly guided experiment. Our DNA may carry not just the history of Earth, but echoes of a much older informational architecture. Oumuamua wouldn't be a lone scout ship, but debris, a fragment of a distribution system billions of years old, mostly dark and drifting, still occasionally doing its job. We already know interstellar objects exist. XNAs work. DNA and microbes can survive years in space with shielding. Error-correcting codes protect our own probes. Planet-scale simulations run on our supercomputers. The wild leap is not in the pieces, but in imagining the motive that ties them together. So what happens next? Do we get a reply? A probe? A warning? Or is our little ping just a new line in some remote archive? Another world reached decoding threshold. Continue observation. Maybe there's no council of elders, no mentors, just an ancient automated process still quietly monitoring what chemistry does when you give it a tiny nudge in a few billion years. If someone scattered seeds like this, then every time life looks up and wonders where it came from, that curiosity itself might be part of the test. So here are the questions left hanging. If our DNA isn't purely ours, but part of a much older design, does that make us less human or part of something bigger? And if the universe really is running one giant slow-motion experiment on life, are we okay being both the subjects and, now that we've glimpsed a fragment of the protocol, the observers?